Can I ask about when the last exam is going to be, or the third exam?
I haven't heard back from Brett yet. I'll keep a talk to him. Then I'll hopefully update everybody on Thursday. Okay.
Okay, and then I was a bit confused. Do we have 3 exams and a final, or is this last exam just going to be the final?
It will be an overview of the whole semester. Okay.
Okay, cool. Thank you.
So the link is now posted in the Zoom chat. You can click on the link to access it. I'm now gonna mute myself on the Zoom, and I'll focus on teaching on the YouTube. If you have any question, feel free to ask. Okay, everybody, welcome back again for another lecture. So in today's lecture, we're going to continue to teach chapter 9, talks about the molecular origin of the elasticity in the rubbery material. So this chapter for me is a very fascinating chapter. And one of the reasons that polymer differs so much with other conventional material like metal, like other ceramic material, is because their unique mechanical property. This is so different with others, and you would only see it in polymer material. So in this chapter, we're going to give some overview of the thermodynamics related to why rubbery material are so different with the rest of the material you actually see and experience. All right, so let's go into today's lecture. So from current. We did a brief overview in the last lecture, if everybody remember, is related to what happens to mechanics and deformation of the polymer. So a quick recap of what we talked about in last lecture, you have to know is what is a deformation of a polymer material. What defines elastic modulus, what defines the Young's modulus, what defines the strain, and what defines the draw ratio. All these are interconnected, so I believe you should have a really good handle on that already, because we have a mechanics class taught in the department related to them. And I expect everybody doing very well in that in the last lecture. So in today's lecture, we're going to talk about something slightly different. And it's kind of some funny cartoon here. But the point is we're going to talk about molecular origin in rubber elasticity. Before I get started, I want to ask everybody a question related to the difference between the rubber and the difference related to our metal spring. A very interesting phenomenon is that rubber and metal behave very differently depending on the temperature. We can probably talk more details in the later part. Let me make sure we're going to cover that. So first is, if you think about a spring, let me use a joint to show everybody what I mean. Let's insert a couple blank slides and talks about it. So if we want to discuss this rubber elasticity, a very interesting phenomenon is called temperature dependent on elasticity. Okay, so if I have put a rubber band, so this is a rubber band, and put about 1 kilograms of a weight in between, at the bottom of it, and hang it On the other hand, I have the same, but it's made of metal spring. And I also have a 1 kilogram of weight put at the bottom. So think about this is now room temperature. If we heated everything up to a higher temperature, let's say imaginable 200 degrees Celsius, and that may be too high, or 150 Celsius. Make sure your rubber band doesn't burn or break. But in that case, what you will see is actually the rubber band will behave totally different with what your metal spring. And this is very important in polymers rubber material. And you will learn in this class why in rubber case you actually will shrink. Your rubber will getting more and more stronger and tougher so that you have a reduced delta L. If your temperature increases, your rubber band actually will shrink and make the rubber more and more stronger. Well, on the other case, if we have a metal spring, the metal spring actually would relax more, where now you have delta L is increased displacement. So in other words, when the temperature increases, the modulus for the rubber band increase. T goes up, E goes up. Okay? While in the metal spring case, when the temperature increases, your spring constant actually go down. And this is due to very different contribution to why metal can act as a spring versus a rubber band act as a spring. Although they behave some sort of similarly, they provide elastic restoration of their initial deformation, but at the fundamental level, they're so different. So why? This is related back to the thermodynamics again, so we're going to briefly review a couple of thermodynamics terms and before we talk about how we can actually use what we learned from the chain conformation to predict the rubber elasticity. And there is a great library of theory and knowledge to help you understand why rubber behave the way they are, and you can actually do very well. You can do prediction of the modulus of rubber material. You can also predict why the rubber depends on the temperature that way and why they are different with metal. So we're going to learn all these in the next 3-4 lectures. So first is why material behave what they are. There are several reasons come into play. There is energy that relate to holding the materials together. It can be covalent bonds, as we mean by carbon-carbon sigma bond or carbon-carbon pi-pi stacking bonds or many other type of the bonds. Those are chemical bonds, or you can hold a piece of plastic together by a covalent bond between a non-covalent bond between the polymer chain. This including all kind of ionic forces if you have ionomer, or van der Waals force and dipole interactions. These are the relatively much weaker force to hold your molecule together. And of course, if you have hydrogen bonding, you can have that. All these contributing the fact that your material will be together as one piece without falling apart. There's also going to be thermal energy that's related to motion of your polymer chain. But these two are generally speaking are what we call in the solid mechanics, the fundamental forces influence your material's property. Okay? But there's also other cases where your random motion will come into play if you heat the materials up. And these two factors are going to be competing with each other, and they play differently in terms of crystalline material versus a polymer chain. In one case, we want to talk about in some of the crystalline structure or a monomer of our polymer structure, or water or any liquids you can think about. At the low temperature, a substance basically behave like liquid, or even the cases they might crystallize to form a solid. But once you heat them up, typically the higher the temperature go, you give the system much more in energy. These are thermal energy, right? So if you heat something really high or heat the crap out of it, they're gonna vaporize, they're gonna even burn. So think about the vaporized case where your molecule has enough thermal energy to break the barrier of these forces holding it together. You know, if you think about there's a tiny chain or handcuffs, you know, holding these together. These are not covalent bond. Those are just a molecular level of interaction, like dipole-dipole interaction or van der Waals. Those are not very strong. If your temperature is high enough, your thermal motion can overcome them and become a gas-like random structure. There is changes in thermal energy. There's also changes in the entropy. So several examples are if you have perfect crystal, like on that, everything is placed in a perfect lattice. That means there's not a lot of disorder and the entropy is low in this case. If you heat up, your entropy goes up. There's also phase transition happens when you heat things up, like you know, melting or vaporization. Those are phase transformation and requires entropy into play, which means you need taking heat. You have a melt entropy. You also have heat capacity need to consider all these factors. But those happens at molecular level if you heat it. You can go the other way around. If you just cool it, it will behave like that. So there's a motion of molecule, something we need to consider. So your molecule cannot move into the next available position unless there's enough thermal energy allows something called a cooperative motion for the polymer chain to happen. What that means is you're going to learn more in the next semester when Sergei Nazarenko teach everybody about the glass transition phenomenon. Briefly speaking, you know, glass transition phenomenon is related to temperature-dependent materials motion. So if you have a glass transition point, if you're above that, that means your molecule has a lot of freedom because it can overcome it has enough free volume for the polymer chain to move around so that it will behave very viscoelastic and very soft. If it's below the glass transition temperature, it will be constrained and behave like a solid-like material. Okay. So, and if you have material crystalline, then it's going to be even difficult for the material to move because every single structure is locked in at a lattice plane. So with that being said, your temperature plays a very vital role in the overall your material's movement and dynamics. There's an extreme case that something we call the foam polymer glass. I'll briefly speaking. So you have two structures in the silicon dioxide. Either it can be for a crystalline structure, we call it quasi, or it have for glass where it's a random structure. So you can see on the right, this is a perfect hexagonal lattice. Well, on the right, this is more random, but those random structures are frozen at the given temperature. So you can think about the inorganic glass, or these windows are made of some molecular that are being vitrified. So at room temperature they want to move, but they are not able to because there are not enough thermal energy. Okay. So for polymeric material, we have similar problem. When we stretch a polymer, what happens? We need to consider the mobility of the polymer with respect to the thermal energy. Okay, so that means give everybody a simple example. Polystyrene at room temperature is very glossy. We know the glass transition point for polystyrene is right about 100 degrees Celsius. So your mechanical response, which is the topic of this chapter, depends very much on what temperature you look at your polystyrene. Is it room temperature? Is it minus 100 degree, or it's 100 degree, or 300 degrees. They all behave very differently. So by changing the temperature, your material can go from glassy state to viscoelastic state to melt and to viscous flow. And your mechanical response and very much depend on that. And there's a unique problem related to the polymer is segment motion and entanglement. And that part is going to be covered more by Professor Yun Simon in the Polymer Dynamics. So I again will not talk too much detail. So in this particular course, we're going to focus on the related, what is the temperature dependence property for polymer and why they could behave like a rubber-like material. Okay? But generally speaking, you need to understand the glass transition temperature and the glass transition phenomenon before you claim your material is elastic or glassy, or it can be deformable or brittle, something like that. So here is some equations that we need to know and master related to the thermodynamics of a rubber material. And that's the fundamental related to how we can derive the rubber elasticity theory. So let me first explain theoretically how people can use rubber elasticity theory. So first, what is a rubber elasticity theory? So rubber elasticity theory is a way that the researchers was able to link the deformation of our polymer chain to a certain rubbery force in our material. What that mean? That means in a metal spring, what it controls it in the rigidity is what's the cross section of your spring? How thick is your spring? That determines how strong. But in rubbery material, it is not governed by the same theory. It governed totally differently using chain conformation theory. In other way, think about a single polymer chain. So what we talked about in a Gaussian coil in the first chapter, everybody knows if you dissolve a polymer, give you example, a polystyrene about a 1 millimolecular weight, if you dissolve it in a acetic solvent, it will behave like a Gaussian coil, right? It's just a coil, and the coil size will be much smaller than its contour length. That means your end-to-end distance is not going to be as big as number of polymer chain multiplied by the bond length. But imagine now there is 2 nanomen. One could be me, one could be you. I holding one of the polymer chain end, you hold the other. Now we start to pull the polymer coil. It was behave like originally a thread, but once we start to deforming it, you would be able to create a deformed polymer coil. What happens in the deformation is you would have lost entropy, because the more we pull it, the number of the end-to-end distance will increase, right? Because we are pulling to end, so end-to-end distance will increase. And you would be able to understand that your entropy will lose because we start to get adding more order. So rubber elasticity theory is exactly the point that how researchers can use your thermodynamics to understand loss of entropy and how that would be related to the force of being pulled to the polymer chain. Okay? So let's get started with the thermodynamics, review some of the fundamental concepts, then we're going to count how does the entropy dependence on different deformation. Use those two information, we will be easily able to achieve what we call the rubber elasticity, is understand how strong a rubber band depends on molecular level structure and chain statistics. Okay, so first is what is the Thermodynamics Law. In the chapter 7 in the polymer solution, we chatted a lot about thermodynamics. I think everybody understands what is the fundamental concept of entropy, enthalpy, but there's also another thermodynamics talks about what is internal energy and how does the internal energy depends on the changes of volume or changes of heat. So generally speaking, this internal volume, delta U, will be dependent on dq plus dW. And dW is the force or the work being down to the system. You can think about an engine. If you have a gasoline engine, you have a certain force exerted on the system, the piston, and it has a displacement. For example, if the piston is moved a certain distance, you have work being down to the system. This, as I mentioned, the work down to the system is related to parts. First, you have pressure change versus volume. So again, use a gas cylinder example. If your gas cylinder expands, there's two factors doing the work to it. First is the expansion of the volume. You have a pressure multiplied by a dV is a volume change. That's what relates to one part of the equation is work down by pressure volume change. And second part is the force displacement change. Actually, these are both are the same. If you think of pressure multiplied by dV, the unit will be similar because pressure multiplied by area will be the force. dV can be deconvoluted area multiplied by displacement. So these two are basically the same. This object explains what is how much work is being done to the system. Okay, that's the first law of thermodynamics. Second law of thermodynamics is basically relating what is internal energy related to the entropy and the work. So you can see, we take a derivative of the internal energy. It can be written as temperature ds. ds again is the entropy change. Temperature multiplied by ds. Pressure multiplied by dV, and dV is a unit volume change. This is a negative pressure. And force multiplied by dl. Force is how much force applied to the system, and L is the displacement. And generally speaking, we can also have another generic relationship. What we know in the last chapter is the Flory-Hagen theory in the thermodynamics, your delta G. Free energy of the system equals to entropy multiplied by enthalpy, H minus the entropy multiplied by the temperature. And if you do a little bit of rewrite, this is basically a more generic term to write delta H is equals to delta U plus PV. And you can get this very generic relationship if you take a derivative of dg. Third derivative, so dg equals to du. So if you have two terms in one, you have to equals to dp multiplied v and p multiplied by dv. That's why you have two terms. And again, the temperature as entropy term will be again break down into two terms. Why we bother, discuss too much of that? Because we want to understand how we can link the force to the entropy loss in the system. So that's where our end goal. And all our discussion is trying to link what is the force F. When we talked about stretching of the polymer coil in a single polymer chain, we want to know how much force I need to pull together with U to make this displacement happen. And we need to understand what would be the entropy contribution of that. So at the end of the day, we wanted to know entropy contribution to the force. And how we get there is showing above, where we have free energy term. This is what we have discussed in the last. And this is the second thermodynamics, first thermodynamics. So the goal is to link what is the force with delta S. So you can see what we need to do is to replace this du term with this new term here. Then some of the part will cancel, pdv will cancel out. And we were left with delta G with VdP minus SDT plus force multiplied by displacement. It's a little bit, how can I say, a lot of thermodynamics in the term inside this simple equation. But fundamentally, as I explained, what we want to do is to link how does the force depends on enthalpy and entropy during the deformation. Okay? So if we take a derivative of dg multiply, that can be written as G, delta P, partial derivative multiplied by dP. What this means? This only replace V because V is going to be a partial derivative of P when fixed at TL. We can write the similar terms, and this is where we can now understand what is the force will be equals to. Force will be a partial derivative delta G, L, and PT. So let me first explain what these two terms on the corner. So P and T on the lower bottom corner means when we fix P and T, your delta G only depends on F and L, and if you take a delta G partial derivative L, you will get force. Same here, if we take this term, when we fix T and L is fixed, T and fixed, there's not going to be dt dl equals to 0, so these two are going to go away. Your dg will be equals to v dp, and v will be equals to basically d delta g partial derivative of p. Okay, and at the end of the day, this is what we need to understand. Force is going to be just the free energy partial derivative to the displacement L at a constant temperature in T. That's all we need for the beginning of our thermodynamic discussion. Then we can expand it to what is delta G is. Delta G is entropy and enthalpy term. We can just add this particular G terms into here. So we know this is going to be equals to H partial derivative L at constant PT and minus entropy and L at constant PT. Okay? So that's all we need to know at this moment. And the next lecture or two, or today's lecture or two, will be discuss about how we can now link the deformation force for a single polymer chain with entropy loss, which is what you can tell. What we're going to do is link this delta S to partial derivative L. What this means, the second term is, let me write again, entropy loss due to deformation. And deformation can be reflected by L. Entropy loss due to L, and this is the enthalpy loss due to the L. So we're going to first talk about first term. The first term, actually, in an ideal case, in a rubber material, no matter how you deform it, the delta H will be constant. So there's not going to be change. But in reality, you still have some loss in the enthalpy. And you can tell when you start to structure a rubber, there is some molecular sliding and friction happens without in heat change. Otherwise, your structuring an ideal rubber band will not cause any heat up or cool down in the rubber material. The second term is entropy, and it will be more interesting. And if you are aware of, there's several things we did in the chain conformation. One is look at chain statistics. How many polymer chain will behave like a Gaussian coil? So we know when you deform it, your chains and configuration status will drop, and we can use that to calculate what is delta S depending on L. So this whole chapter of rubber elasticity theory is based on this yellow equation here. The dependence of force on entropy and enthalpy. Okay? So we're going to go into detail of these. What is individual role they play? So let's first look at enthalpy. Okay? So again, what we show here is a molecular level of interaction diagram. So this is atomic separation distance versus the energy. What this shows at very close distance, this is where we show the bond length. If you have a bond length shows here for between carbon-carbon bond, for example, or any other bond you can imagine, this would be the equilibrium distance. What that means, at this distance, your whole system energy will be lowest. Now, if you start to deform the system uniformly, if we stretch unidirectionally, assume each particle will conform to the macroscopic deformation. This would result in an increase in the distance from R0 to R. To give you more specific number, your R can be maybe 1.5 times of R0. So what that means is, if you look at this energy diagram, this is generic. So if the bond is very far away, it has attraction force. So these forces are in all the attraction region, where it means they want to attract to each other. If you deform them apart, they're gonna come back to where original length is. So you can see this is a deformed bond. The more we stretch, we increase the system energy. Once we release the force applied to it, it will go back. Same for compression is. If we compress them, you can see it's going to be even a sharper increase in the energy, quickly go from attraction to repulsion. So if you place these two green beads really close, they're going to repulse each other and result in a repulsive force. All right? So why this matter to us? This matters because the classical metal spring falls into this category perfectly. If we consider a stainless steel spring, what happens is you never see we use the metal spring as a piece like a rod like this, right? If it's straight rod, you know it's not elastic. If we pull it, first, steel is very strong. You're not going to be able to pull a steel. Second is, even you use a very strong instrument to pull it, it's just going to break brittlely, okay? So you see, that's why all the springs are made into coils. And why they're made into the coil is we're only going to deform each coil slightly. So imagine now in a spring in your cast damping system, your vehicle's damping system, or some of the ball pens, you have a spring inside it. You can see if you pull or compress it, what the displacement happens at each individual molecular level is little. So that's why, because at little displacement for a spring, if you pull it, you'll move the molecule away from its ideal location, then there's attraction force going to pull it back. So you pull a metal spring a little bit away, it's going to come back to where original states. And if you compress it, again, you're going to go the other way, you're going to repulse back. So that's why the metal spring always going to be go back to the original state. This also explains why heating the spring under the load will cause extension, because you'll increase the available molecular motion between different species. So when you increase it, your system will be able to move around more at a given force. Okay? So it is very different with what you will learn in the common chapter related to the rubber material. So briefly speaking, we have also a way to describe what is thermodynamics of metal. If we assume in this locally, your free energy U, R, will be dependent, a constant multiplied by here. Okay? So what this means, this is equilibrium distance, bond distance, R0, what we talked about that. The further you go away, there's going to be an increase of free energy, and this increase is follows a square format. So there's a quick increase in the energy when you displace it. In the first law of thermodynamics, we know that we can take a partial derivative of du with respect to the r to get the constant, spring constant. So you can see F will be taking a partial derivative of u dr. This will be equals to 2 multiplied by c and r minus r0. This is basically the displacement. You know, how far you pull it. And this C is basically the spring constant. So in other words, this explains why a spring would work, because you have force equals to spring constant multiplied by displacement. And you can even write as the modulus and the strain for your material very easily. Okay? We're going to come here. So in the rubber elasticity theory, it's very different with metal. So deformation of polymer takes through a very different mechanism. And that's the beauty of the polymer science, is it's different with metal. If it's already like metal, then polymer is not unique anymore. So although polymer are not as strong, but it's so unique, and you will see why it's unique. The force, as we talked about, this is where we talked about how we can link the force to free energy. Force will be equals to free energy partial derivative of L. So this is entropic term. This is the entropy term with partial derivative. So we typically say there is no entropy difference when you stretch a rubber band. That means you pull or release, there's no heat energy involved, okay? But there's only entropy involved. In reality, it's not that perfect, but it's pretty close. And how close it is, so this is the curve we plot, the force and temperature. And you can see this is the ideal case. The dependence of that is the slope, where you force divided by t. That will be the what described here. That will be what is these two terms added together. So the first top is where this is the entropy, this is the entropy term. So entropy contribution is not zero, but it's near zero and is a constant value and does not depend on the temperature. Well, if you look at the temperature contribution, then it should be a linear curve, because, there is a temperature term, multiply that. So you should always expect this will be a linear for the entropy term contribution, so Fs, and this will be the entropy term. It doesn't have a temperature term, so it should be a constant. This is the theory, or what people expect, and this is what people have actually measured for a real rubbery material. So you can measure stress versus elongation, and this we can further deconvolute into contribution. So this is raw data show into the F curve with a cross here, and they can deconvolute it into entropy contribution. So this is entropy contribution, okay, as shown below. And you can tell it's not perfect, but it's pretty much agrees with one assumption that entropy doesn't play a great role. So I want to stop now today right here, and in the next lecture we're going to explore more details. First is we know that now understanding rubber elasticity comes down to understand what does the force dependence on entropy change. So if you would be able to calculate out what is the entropy change in a rubber band with deformation, you will be able to predict the force. And lucky enough, we spent a whole month in the chapter 6 talked about entropy and chain conformation for a single coil. So here we're going to put it in use. And in the next lecture, we're going to continue and talk about how can we calculate the entropy change from the polymer coil, from a Seda solvent Gaussian coil to pull at a distance L. Okay, if we pull at distance L, we know it's going to expand, and we know how big it will expand, right? The end-to-end distance will be increased from R0 to plus L is whatever displacement we put in. And the question is how much entropy drop is happening during this deformation. As long as we obtain the entropy drop, we can use this very simple, nice equation to calculate what's the force. And we will continue next lecture to discuss that. But it's very nice and beautiful to know that rubber behave very different with metal. One is entropic driven, the other is entropy driven. Okay, so I'm gonna stop the broadcasting on the YouTube and return back to Zoom and answer